Myself, Ketan M. Patel from Mahatma Gandhi Institute of Technical Education and Research Center, Navsari, Electrical Engineering Department. Subject is Electromagnetic Field. Second year, fourth semester. Chapter number 2, Static Electric Fields. Now, syllabus content. First is Coulombs Law, then electric field intensity, then electrical field due to point and line charges, and line surface and volume charges distributions, and Gauss's law and its applications. First, Coulombs law. Coulombs law states that the electrical force between the two charged objects is directly proportional to the product of the quality of charge on the object and inversely proportional to the square of the separation distance between the two objects. F equal to Ke, magnitude of K1 or Q1 into Q2 divided by R square, and F proportional to Q1 into Q2 divided by D square. The other definition of Coulombs law is between 2 point charges there is a force of attraction or repulsion depending upon the nature of charges. Coulombs law, this force is vector quantity which has both magnitude and directions. The magnitude of force between the two electrical charges is given by Coulombs law. Experiments conducted by Coulombs showed that the following hold for two charges that are very small in size compared to their separation, so that they can be considered as point charges. The magnitude of the force is proportional to the product and the magnitude of the charges. The magnitude of the source is inversely proportional to the square of the distance between the charges. The magnitude of force depends on the medium. Thus, if we consider 2 point charges Q1 C and Q2 C separated by distance r meter in free spaces, the force is given mathematically as F1 equal to F2 equal to K2 Q1 into Q2 divided by R square, and its units is Newton. For the free space constant of proportionality is given by K is equal to 1 upon 4 pi epsilon 0, where epsilon 0 is known as permittivity for free space. Its value is epsilon 0 equal to 8.854 into 10 raised to minus 12, approximately 10 raised to minus 9 divided by 36 pi Faraday per meter. We shall use throughout this theory value of 10 raised to minus 10 by 36 pi for epsilon 0, because by using this formula 2 pi's in the expression f gets cancelled, which simplifies the calculations. So f equal to q1 into q2 4 pi e0 r square into its units is n. Now, vector form of Coulombs law. Force is vector quantity and acts along the line joining the two charges. Therefore, the above expression is multiplied by a unit vector along the line. Thus, the vector form force on Q2 is F2 equal to Q1 into Q2 divided by 4 pi epsilon 0 R12 square into A12, while A12 is a unit vector. Same as the Q1 is F1 equal to Q1 into Q2 divided by 4 pi epsilon 0 R21 square into A21. Since A12 equal to minus A21, so we can write F1 equal to minus F2. The unit of force is Newton. Usually in the problems of Coulombs law, positions of the point charges in given charges are given and may be asked to find force on a particular charges. Now, limitations of Coulombs law. The law is applicable only for the point charges at rest. Coulombs law can be only applied in those cases where the inverse square law is obeyed. It is difficult to implement Coulombs law where charges are in arbitrary shape, because in such cases we cannot determine the distance between the charges. The law can't be used directly to calculate the charge on the big plant. Applications of the Coulombs law. To calculate the distance and force between the two charges, and the electric field can be calculated using Coulomb law. Now, electric field intensity. The electric field intensity is defined as a force per unit charge. It is a vector quantity and is denoted by E. So, magnitude of electric field intensity E due to the fixed charge Q at the test charge Q. Here in the figure, the first figure is charge with positive numerical value and second one is charge with negative numerical value. So, E equal to F by Q, or we can say E12 equal to F12 divided by Q, F by Q. So, Q equal Q divided by 4 pi epsilon 0 into R square, or we can say also into A12 unit vector. So, it is also called electrical field strength. Its unit is volt per meter, found by Coulombs law. So, F equal to Q into 4 pi E R square into Q. Another definition of electrical field intensity may be stated as it is the force experienced by unit positive test charge, that is Q equal to 1 coulomb. So, the unit of E is volt per meter, and the kinetic and the electric field intensity at point 2 due to the charge Q1 at point 1 is given by E12 equal to Q divided by 4 pi epsilon 0 in magnitude of R12 square, and into R12 divided by magnitude of R12. Now, in electric field intensity, the space around an electric charge in which influence can be felt is known as electric field. The electric field intensity at a point is the force experienced by a unit positive charge placed at that point. All charges objects create an electric field that extends outward into the space that surrounds it. The charge alters the space, causing any other charges object that enters the space to be affected by this field. The strength of the electric field is dependent upon how charged the object creating the field and upon its distance of separation from the charged object. In these sections, we will investigate the electric field from a numerical viewpoint, the electric field strength. The electric field intensity due to the positive charge is always directly away from the charges, and the intensity due to the negative charges is always directed towards the charges. Due to the point charge Q, the intensity of the electric field at point T units away from its given formula, like electric field intensity E equal to Q divided by 4 pi epsilon 0 into T square. Okay. Now, the motion charge particle in electrical field. If a charged particle of charge Q is placed in the electric field of strength E, the force experienced by the charged particle equal to EQ. The acceleration of the charged particle in the electric field E equal to EQ divided by m. The velocity of the charged particle for after the time t is EQ by m into t if the initial velocity is 0, and the distance traveled by the charged particles is s equal to 1 half into a into t, then 1 half into EQ by m into t2 if the initial velocity is 0. Okay, so now here it is different types of figure to know the value of electric field due to the points and line charges. The electric field intensity at any point due to the system or group of charge is equal to the vector form of electric field intensities due to individual charges at the same point. Here the distance of the point P from its charge Q, and R is a unit vector directed from Qi to point P. Electric field due to the point charge and electric field due to the line charge. The electrical field due to the configurations of sources like a charge, parallel plate capacitor, uniform motions of other charges like a E. Now, use of Coulombs law, E equal to F on Q dash divided by Q dash equal to 1 upon 4 pi E0 into Q by R square. This is away from the Q. In a field diagram, at tail of the vector does not stress. We have seen that the basis of electric charge and Coulombs law in this electric field intensity, electric field lines and its properties. Electric field due to different charges distributions like a point charge, dipole, line of charge, etc. If you recall the previous topics on electric charge and Coulombs law, we can say that the Coulombs law defines the electric force between the two electric charges. When an object of the charges Q1 is placed near another object charge Q2, then Q1 experiences a force which can be determined using the Coulombs law. And interesting questions may arise: how the electric charge Q1 knows the presence of the charge Q2 when separated by distance and do not touch each other. How Q2 can push or pull Q1 by exerting the forces. The answer to all these questions is electric field. Similar to the gravity, the electric field is simply the presence of the charge which represent the region of its influence. Now, what is electric field? The consider a point charges Q1 if another charge is Q2 is brought near Q1, then Q2 experience a force. We know this from Coulombs law. What if Q2 is moved around Q1? Even then Q2 experience the force as shown in the figure. This implies that there is a region second around the charge Q1 where it exerts force any other charges. The region where a charge exerts a force on any charge in that region is called electric field of this charge. According to Coulombs law, the force experienced by charge Q2 due to charge Q1 is equal to F equal to 1 upon 4 pi epsilon 0 Q1 Q2 divided by R square. This electric field N is equal to the force exerted per unit charge. It is a vector quantity denoted by the direction of this vector is line joining Q1 and Q2. The electric field around its charge object is represented using the imaginary lines of force called electric field lines. For a positive charge, these lines spread radially outward from the charges. In contrast, for a negative charge, the lines are directed inwards towards the charges. Now, electric field due to the different type of charge distributions. Let us see how we can determine the electric field due to different types of charge distributions. For the point charges, electric dipole, line of charges, and charge disk. Point charges. This is very simple and we have already seen the equations of point charges. But let us find the electric field due to the point charges. Assume a point charge Q. Let us place another charge Q0 at a distance r from the point charge. From the Coulombs law, the electric force acting on the test charge is given by the equations. F equal to 1 upon 4 pi 0 into Q and Q2 divided by R square. Now, some general statement that can be made about electric field lines. Every electric field line begins either at infinity or at a positive source charges. Second one is every electric field line ends either infinity or at a negative source charges. And third one is electric field lines never cross each other or themselves. Now, In electric field, due to point and line charges, the result will show the electric field near a line of charges fall of us where a distance from the line. Assume we have long line of length which total charge is q. Assume the charge is distributed uniformly along the line. So the total charge on the line, the charge density is coulomb per meter square. In line charge density, rho L equal to dq by dl. dq means differential charge and dl means differential length. And its unit is coulomb per meters. Charge rho L on z axis and point rho L on z axis at any point like 0, 0, z on the z axis. A differential amount of charge dq equal to rho n into dl is present. So since the charge lies on the z axis, dl equal to dz, hence dq equal to rho L into dz. So the point 2 rho phi and z dash be the point at which the electric field intensity is desired. So E equal to rho L 2 pi E0 rho L into AS. Okay. Now, in this figure, these are the different types of electric field models. Here it is a first is good approx for small charge object real wire, and the Coulombs law equations is F1 on 2 and F2 on 1 equal to K Q1 into Q2 divided by R square, and K is equal to 1 upon 4 pi into E0, and E due to the point charge E equal to 1 upon 4 pi E0 into Q by R squares. It is the electric field of a point charge. And limiting case, check the simpler formula like E points charge very far. Okay. Now, line surface and volume charge distributors. Here it is a different types of distributions charges, point charges, line charges, surface charges and volume charges. Okay. Now the continuous charge distribution system is a system in which the charge is uniformly distributed over the conductors. In continuous charge systems, infinite number of charges are closely packed and they have minor space between them. Unlike from the distance charge system, the continuous charge distribution is uninterrupted and continuous in the conductor. There are three types of continuous charge distribution systems. With the help of Coulombs law and superposition principle, we can easily find out the electric field due to the system of charges or discrete system of charges. The word discrete means where each charge is different and has extents of its own. Suppose a system of charges having a charge q1 and q2 up to qn, we can easily find out net charge by adding charges algebraically and net electric field by using the principle of superpositions. So because a discrete system of charges is easier to solve and discrete system of charges do not involve calculus in calculations. But how to calculate electrostatic terms in continuous charge systems? For an example, if there is a rod with a charge q uniformly distributed over its and we wish to find the electrical field at some distance r due it would be illogical and irrelevant is simply add electrical field using the principle of superposition as the charge is uniformly distributed over the rod. So we take small element of the rod and integral it with proper limits. We consider elements based on the how density of charges is centered on the material or object. If the charge is uniformly distributed over the surfaces of the conductors, then it is called surface density. If the charges varies linearly along the length of the conductor, then it is called linear charge density. And if the charge changes the volume of the conductor, then it is called volume charge density. So here it is point charge, line charge, surface charge and volume charge distributions. Now here the different types of charge distributions. First is line charge. It is denoted by this lambda, line charge density. So value del q by del I. Del I is a small wire line element that includes microscopic charge components, and del q is a charge found in the line element, and its unit is C by m. Next is surface charges is rho, surface charge density. Del q by del s into del s is in area element on the conductor surface, and del q is a charge in that element. Its unit is coulomb per meter squares. Next, volume charge is rho, volume charge density. Del q by del v. Del v is a volume element that includes the large number of microscopic components, and del q is a charge on the elements, and its unit is coulomb per meter cube. In surface charge density, in line charge density, when the charge is not uniformly distributed over the length of the conductor, it is called linear charges distributions. It is also called the linear charge density and is denoted by the symbol of lambda. Mathematically linear charge density is lambda equal to dq by dl. In surface charge density, when the charge is uniformly distributed over the surface of the conductor, it is called surface charge density, or we can say surface charge distributions. It is denoted by the symbol of sigma and the units of coulomb per meter cube square. So sigma equal to dq by ds. And volume charge density, when the charge is distributed over a volume of the conductor, it is called volume charge distributions. It is denoted by symbol rho. In other words, charge per unit volume is called volume charge density, and its unit is coulomb per meter cube. Its mathematically volume charge density is rho equal to dq by dv. Okay, so these are the different types of distribution charge of line, surface and volume. Now, Gauss's law and its applications. According to the Gauss's law, the total flux linked with a closed surface is 1 upon epsilon 0 times the charge enclosed by the closed surfaces. Here Q equal to phi into epsilon 0. The Gauss's law formula is expressed by the phi equal to Q by epsilon 0, where the Q is a total charge within the given surface and epsilon 0 is a electric constant. The electric field is the basic concept to know about electricity. Generally, the electric field of the surface is circulated by applying Coulombs law. But to calculate the electric field distributions in a closed surface, we need to understand the concept of Gauss's law. It explains in the electric charge enclosed in a closed or the electric charge presence in a enclosed the closest surfaces. In Gauss's law formula, as per the Gauss's theorem, the total charge enclosed in a closed surface is proportional to that the flux enclosed by the surfaces. Therefore, if phi is a total flux and epsilon 0 is a electrical constant, the total electric charge Q enclosed by the surface is S. So Q equal to phi into U is epsilon 0, and the Gauss's law formula is expressed by phi equal to Q by 0. Okay. Now, in Gauss's theorem, the net flux through a closed surface are directly proportional to that the net charge in the volume enclosed by the closed surface. So Q equal to ED and A and Q divided by epsilon 0. In simple words, the Gauss theorem relates the flow of electric field lines, or we can say flux, to the charges within the enclosed surfaces. If are no charge enclosed by a surface, then the net electric flux remains 0. Okay. Now, in Gauss's law in magnetisms, the net flux for the surface on the left is non-zero as it encloses a net charges. The net flux for the surfaces on the right is 0 since it does not enclose any charges. The important point is the law Gauss's law is only a restatement of the Coulombs law. If you apply the Gauss's theorem to a point charge enclosed by a sphere, you will get back the Coulombs law easily. Now, applications of Gauss's law. First is electric field due to an infinite long straight charge wire. Second one is electric field due to infinite charge plan sheet. Third one is electric field due to two parallel charges sets. Fourth is electric field due to uniformly charged spherical cells. And fifth one is electrostatic shielding. In electrical field due to infinite wire, Gauss's law application is consider an infinitely long line of charge with the charge per unit length being lambda. We can take advantages of the cylindrical symmetry of these situations. By symmetry, the electric field all point radially away from the line of charges. There is no component parallel to the line of the charges. So we can say use of cylindrical with an arbitrary radius r and length is L, center on the line of charge as our Gaussian surface. Okay. Now this is all the importance theory of the chapter number 2. Thank you.